The pod is small. One body lies inside it, connected to monitoring lines, breathing steadily in the dark. The spacecraft around it has been stripped to its essentials. Outside the only viewport, the sun has become a hard white point among the stars. Science fiction has a name for this image: Cryosleep. The crew lies down, the ship crosses the distance, and the travelers wake at the destination as though an afternoon had passed. The journey becomes someone else's problem. Real research does not support that version. It talks instead about torpor, induced hypothermia, and metabolic suppression, reduced metabolic states that are slower, medically complicated, and far more limited than a cinematic cut to the destination. So the question is real: could any version of that actually make deep space travel more practical? By the end of this video, you will know what part of that idea is real science, and why sleeping through space may reduce what the spacecraft costs, while leaving the body problem open. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Look at the pod through its window. Inside, a face is faintly visible, not blue-white and crystalline in the way science fiction draws it. The chest moves with shallow, steady rhythm. Sensor leads trail from the wrist and collarbone, and the display on the pod frame shows the body is still running, only much more slowly than usual. That single observation, alive and monitored, not frozen and inert, is where the whole subject has to begin. Because the most important question about sleeping through space is not simply whether humans can do it. It is whether the version being discussed is the cryosleep of science fiction or the genuine and far more limited biology of torpor. Those are not the same claim, and the difference between them is not a minor technical detail. Science fiction has a name for this image: cryosleep. The crew goes in, the distance passes, and the journey is over. It is a clean, comfortable image, repeated so many times it has started to feel like a technical category rather than a dramatic convenience. No version of that is available in current science, and it is worth understanding why the biology makes it so difficult. Cryopreservation is the technical word for freezing and storing living material. It works under very specific laboratory conditions for small structures like individual cells or simple tissues, where ice formation can be managed precisely enough to allow recovery. For a whole adult human body, the challenge is fundamentally different in kind. Ice is not gentle at the biological level. When water freezes inside complex living tissue, it expands and tears cell membranes, concentrates salts and proteins to damaging levels, and disrupts the spatial geometry that cells depend on to function. The adult human body is precisely interconnected in ways that ice formation cannot uniformly damage and then repair during thawing. And no demonstrated technique exists for cryogenically freezing a healthy adult human and subsequently recovering that person. That is one corner of the vocabulary. Torpor occupies an entirely different corner. Torpor is not freezing, it describes a managed reduction in metabolic rate, with body temperature dropping and energy demand falling accordingly. An animal in torpor has not paused. Its metabolism still runs at a fraction of normal speed, and the animal remains regulated and intact throughout. That distinction is foundational. Cryopreservation proposes stopping biology and restarting it later, while torpor proposes slowing biology and allowing it to keep running at a reduced rate. These are not two positions on the same line, leading to the same destination, but different biological claims with different mechanisms, requirements, and prospects for application at human scale in a spacecraft. Hibernation adds one more layer of detail. In hibernating species like ground squirrels, the winter pattern is not one long sleep, but a structured cycle of torpor bouts and brief arousals. The animal enters the reduced state for days or weeks, then warms slightly to adjust its chemistry before returning. That cycling continues throughout the season, with the animal's own biology managing the entire process from within. Induced hypothermia is a medical term that belongs to intensive care rather than spaceflight engineering. Used in hospitals after certain cardiac events to limit secondary tissue damage, It is a procedure measured in hours under continuous clinical monitoring. Cryopreservation, torpor, and induced hypothermia all share the general concept of a body operating at reduced speed. Everything else about them differs: the mechanism, the required monitoring, and the engineering demands of a vehicle far from any hospital. The vocabulary confusion persists partly because each of these terms describes something genuinely real. Cryopreservation works at the level of cells and simple tissues and is fundamental to modern medicine. Clinical hypothermia works under supervision over hours and saves lives after specific acute injuries. Torpor works in species that evolved to use it and produces remarkable physiological results in those animals. None of these is a fiction within its proper domain. The problem arises when popular writing treats them as three positions on a single line, leading to the same destination. They are not on any line together. The mechanism is not a detail to be resolved later. It is the substance of the problem itself. Whether metabolism is stopped, slowed, or managed under short-term supervision determines what pharmacology is required and what monitoring hardware must be aboard. It also determines what biological risks are present and how far current science can take the concept. A spacecraft architect cannot choose the right design without knowing which mechanism is being targeted. A policymaker cannot assess readiness without understanding which specific biological capability has and has not been demonstrated. Starting with clear vocabulary is the minimum requirement for having an honest conversation about what is and is not achievable. The research that carries genuine weight is not at the cryopreservation end of this spectrum. It is a more cautious and medically grounded question whether something closer to torpor, a managed reduction in metabolic activity accompanied by lower body temperature and reduced consumption, might be achievable and safely maintained in humans for weeks or months under appropriate clinical management. That is where ESA has done serious architectural thinking and where NASA and SpaceWorks have studied mission designs. They are not designing frozen passenger chambers, but asking a more limited and more honest question. If a crew could be maintained in a reduced metabolic state through part of a mission transfer, what would change about the spacecraft around them? That framing keeps the engineering problem real. The actual engineering target is not that movie version. It involves pharmacology, thermal management, and biology that remains genuinely unresolved in human subjects. There is another phrase that sometimes enters these discussions: suspended animation. It does not have a precise biological definition and tends to borrow its meaning from whichever end of the spectrum the speaker prefers. The practical requirements of those two ends are completely different. When you encounter the phrase, the useful question is which actual claim is being made. The reason this vocabulary matters so much is that each label carries a specific set of required capabilities. If cryopreservation at full human scale were the goal, the answer would be short. The biology is not there. If managed torpor-like dormancy is the goal rather than cryopreservation, the problem becomes harder, stranger, and potentially far more interesting. It requires understanding what the body can tolerate, what animal physiology suggests about the limits of low metabolic states, and what a spacecraft must do when most of the human capability aboard it is unavailable for months at a time. The pod window shows something harder to build and harder to reverse than anything in a movie, a body that is alive, monitored and slowed, not a frozen artifact or a passenger who has stepped out of biology, but a living system reduced to a fraction of its normal activity. That is exactly what makes it a real engineering question worth examining carefully. The real version is more limited than the cinematic version. Metabolism is reduced rather than stopped. The monitoring requirement is higher rather than lower, and the biology continues quietly beneath the surface. And yet, serious research groups and space agencies have invested real effort in asking whether that harder, more limited version might still be worth attempting. If the real version is more limited than the movie image, why do engineers still care about it? Picture a spacecraft floor plan. Not the whole vehicle, but the crew section, the portion where 6 people would live for months during a Mars transfer. In a conventional mission design, that volume has to support daily life. The crew needs space to sleep privately, prepare and eat meals, exercise with meaningful resistance, and maintain enough common area to stay functional over months. The mission also needs storage for food, water and medical supplies across a 9-month mission, enough physical and psychological space to keep 6 people functional and reasonably intact during what could be one of the most isolated and demanding experiences humans have ever undergone. Now picture the same spacecraft designed around 6 torpor pods instead of a full habitat. ESA's concurrent design facility examined exactly that trade, modeling a 6-person Mars and back mission with a projected 180-day Earth-Mars cruise phase under assumed drug-induced torpor conditions, and adjusting spacecraft architecture to understand what followed from a mostly inactive crew. The numbers reward attention. Under the study's assumptions, spacecraft mass could be reduced by roughly 1/3 by eliminating the crew quarters and active use facilities required for a fully awake crew. Consumables drop substantially when 6 people are not eating and exercising actively for 6 months of transfer. Habitat concepts for an active deep space crew typically run into hundreds of cubic meters of pressurized volume. The Hibernation architecture version can work with a much smaller fraction of that, because the crew is not living in the space in any active sense, they are being maintained in it. NASA and SpaceWorks explored similar territory through the NASA Innovative Advanced Concepts program, proposing a torpor-inducing transfer habitat for 4 to 6 crew in individual pods. Total habitat mass in the concept came to roughly 5 to 7 metric tons, against 20 to 50 metric tons in conventional designs, with proposed volume at around 20 cubic meters against roughly 200 cubic meters in most conventional active crew concepts. These figures are architectural projections based on assumed conditions, assumed torpor capability, assumed autonomous medical monitoring, assumed drug-induced metabolic suppression over the full cruise duration. None of it is demonstrated mission hardware or validated flight technology, but the numbers reveal the engineering motivation plainly. A spacecraft that is 1/3 lighter costs substantially less to launch. That difference changes the launch configuration required, which changes the propellant budget, which changes the mission architecture from the initial mass equations forward. A habitat 1/10 the volume transforms the structural mass, the thermal management requirements, and the downstream design of everything that follows. That is why engineers care. Not because anyone has a working torpor chamber or demonstrated long-duration human metabolic suppression, because the arithmetic of getting humans to Mars, or anywhere meaningfully farther, is extremely punishing under conventional assumptions. Every kilogram added to a deep space mission multiplies the propellant needed to move it, which adds mass for the propellant, which requires more propellant in turn. Habitat volume drives structural mass, consumables have weight, and crew activity requires systems to support it and power to run them. A crew that is mostly inactive for part of a long transfer, if it could be managed safely, changes several critical lines of that calculation simultaneously. The shielding geometry shifts in an interesting way too. In a conventional habitat, living volume is distributed across the spacecraft because the crew needs space to move, work, and live. Concentrating mass-efficient radiation shielding around a distributed habitat is difficult because there is too much surface area to cover at practical mass. In a torpor architecture, all 6 crew members spend the transfer inside one small, closely clustered volume. ESA notes this advantage. Shielding, water containers for example, can be concentrated around the pods because the crew are always there. That concentration is only achievable when the crew stays in one place. A savings category harder to quantify, but real at the human level, also exists. Long missions are not only a mass and volume problem. Months of active confinement, with limited communication back to Earth, and the constant weight of mission responsibility produce measurable effects on crew performance and well-being. Fatigue, interpersonal friction, and sleep disruption all accumulate in ways that show up in crew performance. A crew in a managed torpor state does not navigate those pressures during the cruise phase. The accumulated psychological cost of 6 months of active confinement is effectively avoided for the duration. This kind of savings does not appear in a mass budget, but mission planners track it because deep space crew performance at destination matters enormously. The science work, the landing operations, the surface mission, and any contingencies require crew members who are as capable and as rested as possible. A technique that arrives the crew at Mars with 6 months less of accumulated confinement stress has value beyond the habitat mass it saves. Consumption arithmetic reinforces the picture. All consumable supplies scale with the number of active person days on the mission. A crew inactive during a 180-day cruise requires a very different supply chain for that phase than a crew fully active for the same period. Even if the torpor pods themselves require continuous power and some consumable support, the savings in crew provisions are real. ESA also identifies an expectation from animal hibernation that crew members in torpor might avoid some of the bone and muscle deterioration that normally accumulates during extended microgravity exposure. This expectation is drawn from animal evidence, not demonstrated in human microgravity torpor studies, and it deserves to be held carefully. But if any fraction of that biology translated, the crew would arrive at Mars requiring less rehabilitation before mission-critical work could begin. What all of this amounts to is not a promise of a working system. It is a set of architectural incentives strong enough that serious engineering groups have found the concept worth studying even before the biology is resolved. The spacecraft gets smaller, lighter, and possibly better shielded. The crew consumes less, accumulates less confinement burden, and may arrive in better condition than they would after months of active confinement. The mission design also benefits from the concentration of the crew in another way that is easy to overlook. In a conventional habitat, crew members are spread across the spacecraft for most of the transfer. Safety systems, fire suppression, emergency pressure suits, and evacuation pathways have to be distributed through the entire habitable volume. In a torpor architecture, where all crew are in one small pod cluster, many of those safety systems can be concentrated around that volume instead of distributed through a larger habitat. The simplification is not trivial from an engineering and mass perspective. None of this changes the fundamental requirement. The architectural incentives are powerful enough to explain why agencies have studied the concept seriously. The biology still has to be demonstrated before any of those savings become real, but the incentives are worth understanding clearly because they explain why this is not a fringe idea or a science fiction hope. It is an engineering argument made by the people who design spacecraft for a living based on mission arithmetic that is real and unforgiving. The spacecraft can shrink on paper only if the body can safely slow down in practice. Watch the monitor beside a hospital bed. The display shows temperature and cardiac rhythm, among other readings, all measured in continuous loops. The patient in the bed is cooled to a few degrees below 37 Celsius by a controlled external system, carefully watched and pharmacologically supported. This is the closest real human analogue to what torpor concepts require, not a space chamber, an intensive care unit. And the gap between that clinical setting and an autonomous deep space habitat is not a matter of improving the equipment. It is a matter of rethinking what makes the clinical version survivable in the first place. The physics of cooling and metabolism are connected in a way that gives the concept a real foundation. Lowering core body temperature reduces the rate of biochemical reactions throughout the body. The relevant clinical figure is roughly a 5 to 7% reduction in metabolic rate for each 1 degree Celsius drop in core temperature. A body cooled by 5 degrees runs at roughly 70 to 80% of its normal metabolic pace. For a spacecraft trying to reduce oxygen consumption, heat output, and nutritional demand, a meaningful metabolic reduction is a genuine architectural benefit, but there is a significant distance between a useful number and a workable system. Controlled hypothermia, the deliberate reduction of core body temperature in a medical context, is a real intervention with a real record. Targeted temperature management is used after some cardiac arrests and certain neurological injuries particularly events where reducing metabolic demand during a critical window can limit secondary damage to brain tissue. Clinical evidence supports its use for improving neurological outcomes after specific cardiac events. It saves lives, and that is why it has become part of critical care. The conditions that make it clinically useful also define the distance from any space application. A patient undergoing therapeutic hypothermia is in an intensive care bed with continuous monitoring of cardiac rhythm, temperature, and blood chemistry. Electrolyte balance requires active management because cooling shifts ion distribution, and the rewarming process must be controlled carefully to avoid instability and rebound complications. None of that monitoring is incidental. The clinical burden of keeping a cooled human being stable is substantial, and the window during which it is applied is measured in hours to at most a day or two, not in months. The patient is in a hospital because they require a hospital's worth of continuous support to survive the process. For a spacecraft application, this creates a hierarchy of challenges. The first is duration. Clinical hypothermia is applied for hours during a specific injury window. Extending that to a 180-day cruise phase involves biological assumptions untested in any human subjects, and the metabolic reduction that buys time after cardiac injury is not the same physiological state as multi-month managed dormancy. The closest comparison in medicine is long-term sedation in intensive care, and that literature is primarily a record of complications: muscle wasting, delirium on waking, and prolonged recovery. The deeper challenge is the monitoring requirement itself. Clinical hypothermia works because the patient is never unattended. In a spacecraft where the entire crew is in torpor pods, there is no crew left to respond if a pod alarm activates 7 weeks into the cruise. Every monitoring function, every alarm assessment, every intervention decision would have to be handled by automated systems operating without human oversight or the ability to call for help. That is not a refinement of a medical device. It is a different category of system entirely. Ordinary hypothermia, the uncontrolled kind that results from cold exposure, is not a useful comparison point. Uncontrolled cooling does not produce the tightly managed metabolic reduction that clinical protocols achieve. It produces a cascade of physiological failures, with the body losing normal warming responses below 35 degrees Celsius, serious arrhythmia risks appearing below 32, and ventricular fibrillation becoming likely below 28. These thresholds are precisely what clinical cooling protocols are designed to stay above, which is why uncontrolled cold exposure is a medical emergency rather than a rest state. A torpor concept for spaceflight would not involve cooling a crew to those dangerous ranges. The practical zone being studied is narrower, a few degrees of controlled core temperature reduction, carefully maintained, with the crew's own biological regulation doing much of the homeostatic work. That is conceptually closer to the upper end of natural animal torpor than it is to clinical hypothermia in its deeper ranges. But it is not a demonstrated human capability. It is a biological aspiration that draws on evidence from other species and from the limited human medical record. What clinical hypothermia actually offers the space medicine question is a confirmed foothold. The human body can tolerate short-term controlled cooling under intensive supervision, and doing so demonstrably slows metabolic demand. That is a real and useful piece of evidence. It confirms that the metabolic pathway being targeted actually works in humans. The body does slow down when cooled, and in the right clinical setting it can be brought back safely. The clinical baseline also defines what autonomous spacecraft systems would need to replace. Therapeutic hypothermia requires continuous cardiac monitoring and active management of electrolyte balance. It also requires temperature regulation within a narrow window above the thresholds where dangerous cardiac arrhythmia becomes likely. Any spacecraft system doing equivalent work needs those same capabilities built into automated hardware, running without clinical staff and without the ability to request outside assistance. The clinical record does not only confirm that cooling is biologically possible, it specifies the minimum viable monitoring and intervention toolkit that an autonomous system must replicate before the approach could be considered safe for an unattended crew in deep space. That specification is useful because it is concrete. It moves the autonomous monitoring requirement from an engineering abstraction to a defined set of physiological measurements that must be tracked and a defined set of intervention capabilities that must be available. The question becomes not whether automated monitoring is conceivable in principle, but whether it can be made sufficiently reliable over months rather than hours in a radiation environment without access for maintenance or repair. What clinical medicine does not offer is a blueprint for autonomous multi-month dormancy. The monitoring burden requires a level of constant attention that medicine has only delivered through staffed care environments. The biological effects of sustained moderate cooling in humans over weeks or months under microgravity and radiation are not described anywhere because no human has experienced that combination. The pharmaceutical tools for inducing a sufficiently deep torpor state in a healthy adult without the injuries that normally motivate clinical hypothermia do not exist in any tested form. Human medicine can reduce metabolic demand through cooling. That much is established and the physics is clear. The cost is an intensive care infrastructure running continuously without staff capable of intervention in a closed environment weeks from Earth. That is a hard requirement to satisfy inside a vehicle where the entire purpose of the exercise is to have fewer active people managing anything. Humans are not natural hibernators. The medical record says cooling works, but only under intensive care. And intensive care in deep space, with no one awake to provide it, is a problem that has not been solved. If humans cannot manage this on their own, and medicine can only do it under supervision, the only remaining reference is the biology of animals that actually hibernate. That evidence has to explain why researchers keep looking at the problem. The animal lies curled in its den, breathing perhaps once or twice a minute. Its heart beats a handful of times per minute instead of the hundreds that mark its active state. Core temperature has dropped to just a few degrees above the surrounding air. Metabolism is running at perhaps 5% of its summer rate. The animal has been this way for weeks and will remain so for weeks more, cycling briefly into shallow wakefulness and then returning to the deep torpor state. When spring arrives, it will emerge with muscle and bone largely preserved, cardiovascular function ready to ramp back to full speed within hours. Hibernation, as biology actually produces it, has nothing dramatic about it, not a crisis or a malfunction, a carefully regulated, genetically encoded physiological program that some species execute as their normal winter strategy. For researchers interested in the space problem, this kind of biology is the most important reference available. Natural hibernation demonstrates that mammalian physiology can manage states of prolonged metabolic suppression in a way that would be extremely difficult to replicate through external medical control in a non-hibernating animal. The hibernator coordinates metabolic suppression, cardiovascular adjustment, and muscle preservation across weeks-long cycles without continuous external monitoring and without pharmacological support. Its body runs the program from within. Understanding how hibernators accomplish this is an active area of investigation. Some of the mechanisms are now clear enough to study at the molecular level. During torpor bouts, hibernators dramatically reduce cellular metabolic activity. Protein synthesis slows sharply. Energy use shifts almost entirely to fat burning. Ion channels and membrane properties change to keep cells stable at temperatures that would disrupt the function of most non-hibernating mammalian tissue. Cardiovascular regulation adjusts to maintain blood flow at much lower rates without producing the clotting, organ damage, or pressure injuries that would follow in an inactive, non-hibernating mammal. Immune function enters a modified state that appears to suppress the inflammatory responses that would otherwise cause tissue damage during prolonged immobility. One thread in this research is particularly relevant to space medicine. Studies into hibernators and radiation biology have found that some hibernating species show remarkable tolerance to radiation doses that would be severely damaging to active mammals of comparable size. Ground squirrels have been examined in this context, and the evidence suggests that during torpor bouts, certain cellular damage response and repair pathways operate differently than they do in the active state. The hibernating animal appears to have some degree of radio resistance during torpor that it does not show when active. Radio resistance during torpor, if it translates to humans, would add a second layer of protection on top of mass savings. But the scientists who work in this area are careful about how far the evidence extends. The mechanism behind hibernator radio resistance is not fully understood. It appears to involve the combination of reduced metabolic activity, the lowered temperature, and some aspect of the modified cellular state during torpor. How the specific molecular pathways produce the observed protection is still being worked out, and there is a more fundamental gap between the laboratory evidence and the space application. The radiation exposures studied in those experiments involve acute high-dose irradiation, controlled doses applied in a research context to measure the animal's response. The radiation environment of a deep space transfer is different in character. Chronic, low-dose rate exposure to galactic cosmic rays over months, combined with the unpredictable possibility of solar energetic particle events. Whether hibernator radio resistance during acute high-dose exposures tells us anything useful about chronic low-dose rate protection during a Mars cruise has not been established. The research literature explicitly notes that protection against chronic deep space radiation in torpor states is currently unknown. That distinction matters for mission planning. Evidence of acute radiation tolerance in hibernating rodents is useful laboratory data, but it does not translate directly to the chronic radiation environment of a 6-month interplanetary transfer. These are different biological questions, and answering one does not answer the other. Synthetic torpor research adds another dimension to the animal picture. It turns out that torpor-like states can be induced experimentally in some non-hibernating mammals. Certain interventions, from adenosine receptor activation to pharmaceutical cocktails targeting metabolic regulation, can push laboratory rodents into a torpor-like state even though rodents are not natural hibernators. The animals reduce metabolism, lower body temperature, and enter a state recognizable as torpor by metabolic and physiological measurements. For the space medicine question, the finding is significant. If the machinery for managing a low metabolic state is present across mammalian biology, including in species that do not naturally hibernate, then it might be possible to trigger something similar in humans through appropriate intervention. The idea is not obviously futile. Biological pathways exist to work with. But the scale of the gap between a laboratory experiment in a rodent and a 6-month human mission is enormous. Rodents are not humans, and a brief induced torpor state in a controlled laboratory setting is not a sustained mission phase. Triggering a state is not the same as maintaining it safely over weeks and months. Waking a rodent in a laboratory under normal conditions is not the same as waking a crew member in deep space who may need to assess an anomaly, operate equipment, make a medical decision, or simply recover enough to function after an extended period of metabolic suppression. Laboratory conditions are controlled and reversible in seconds, while mission conditions are none of those things. The animal evidence does not promise that human torpor is achievable in a mission context. What it offers is something more limited and still genuinely useful. It establishes that biology can manage remarkable low metabolic states in natural hibernators, and that some of the machinery for doing so may be present in mammalian physiology more broadly than in just the hibernating species. It demonstrates that the hibernation benefits, preserved muscle and bone alongside maintained cardiovascular function and possibly radiation tolerance, are real biological phenomena rather than science fiction inventions. For researchers and engineers studying space torpor, the animal evidence matters because it maps the territory. It says, evolution has solved a version of this problem before, and the solutions are not fictional. The biology exists. Whether any of it can be reliably reproduced in a human being over a deep space mission duration, under autonomous pharmacological management, is the open question. The animal evidence does not resolve it, but it gives the question a biological foundation solid enough to be worth studying seriously. The gap from animal evidence to human mission capability is where most of the real work remains. Synthetic torpor in non-hibernating rodents has been demonstrated in the laboratory. Limited human metabolic suppression under intensive clinical care has been demonstrated. That combination, safe and reversible multi-month torpor in a human under autonomous management in a spaceflight environment, remains a research goal without a demonstrated solution. The biology of hibernation is real and it is remarkable. The translation to astronauts is unresolved. Even if metabolism can be lowered, deep space radiation is still outside the pod. Galactic cosmic rays carry no sensation with them. No sound, no heat, no visible light. They pass through spacecraft walls and the resting body inside, depositing small amounts of energy in tissue along each path, and accumulating in the cells of a crew that has no awareness of the exposure and no ability to interrupt it. The spacecraft moving quietly through deep space with a dormant crew inside is still a radiation environment. The particles do not wait for the crew to be awake. Radiation is one of the fundamental constraints in deep space human travel, and it does not change because the crew is asleep. NASA's RIDGE framework groups the major risks of long-duration spaceflight, with space radiation listed first for a reason. It represents one of the most significant unresolved hazards for any crewed mission beyond low Earth orbit, and it sits at the center of the Mars mission human health question in ways that no current technology has fully answered. The radiation environment in deep space separates into two distinct problems for a transit crew. Trapped radiation in Earth's magnetic field is a concern in low orbit, but largely disappears once a spacecraft leaves that boundary. Galactic cosmic rays are the chronic background that matters for transit, a near-constant flux of high-energy nuclei streaming through the solar system from distributed galactic sources. These are the hardest component to address. The same energies that carry them across interstellar distances let them pass through ordinary shielding with relatively limited attenuation, and very thick shielding can create secondary radiation through particle interactions that in some cases adds to the dose rather than reducing it. Solar energetic particle bursts add an episodic hazard on top of this chronic background. Over a 6-month cruise phase, a Mars-bound crew accumulates a radiation dose from this chronic background that is meaningfully higher than what astronauts receive on the International Space Station during a comparable period, because the station is inside Earth's magnetic field and the transit is not. NASA's assessment identifies radiation exposure as a central health risk for Mars missions, connecting cumulative dose to cancer risk and cardiovascular effects that become more significant with each additional month of exposure. Now, consider what a torpor state actually changes about this situation. The ESA architecture study notes one genuine etch geometric benefit. If all crew members spend the cruise phase in a small, clustered volume inside the habitat, rather than moving through a large conventional habitat, radiation shielding can be concentrated around that volume more efficiently. Water is an effective moderate density shielding material, and a thick water layer around 6 closely grouped pods uses the available shielding mass more efficiently than the same mass spread around a larger habitat. The geometry of torpor architecture creates a configuration where the crew is always in the best shielded location. Pod concentration creates a real architectural advantage. It follows directly from clustering the crew, and it represents one of the genuine ways that torpor design could reduce radiation dose compared with a conventional mission architecture for the same shielding mass investment. But concentrated shielding does not eliminate the galactic cosmic ray background. The most energetic components of the cosmic ray flux pass through any practical thickness of spacecraft shielding. For a 6-month cruise, even with optimized shielding geometry and the best available materials, a crew accumulates a radiation dose that mission planners have to account for as a real health consequence. Sleeping through the journey does not reset or reduce that physical accumulation. The particles traverse the same distance through tissue whether the person inside is awake or dormant. The animal evidence adds a thread here that is scientifically interesting and genuinely relevant. Research into hibernating species has found evidence that some hibernators show increased tolerance to radiation exposure during torpor bouts compared with their active state. Studies in ground squirrels and related species suggest that during the torpor state, certain cellular damage response pathways operate differently, with a combination of reduced metabolic activity and the physiological state of torpor appearing to provide some degree of protection against acute radiation damage. If a mechanism of biological radioresistance operated in a human torpor state during a Mars transfer, the crew would benefit in two ways simultaneously: a reduced geometric dose due to pod shielding concentration, and reduced biological damage per unit of dose due to the torpor physiology. That combination, if it worked, would represent a meaningful compounding advantage. The research is careful about how far this evidence extends. The radioresistance findings come from laboratory studies involving acute high-dose exposures applied to animals in torpor, while the deep space environment is different in character. Chronic low-dose rate galactic cosmic ray exposure over months, rather than a controlled single dose. Whether the hibernator radioresistance under acute conditions says anything about chronic low-dose rate protection during a Mars cruise has not been established, and the research literature explicitly notes that it is currently unknown. Solar particle events create a separate management challenge, since a major burst can deliver a significant dose over hours. An active crew on the International Space Station can seek shelter in the most heavily shielded module when a particle event is detected. A crew in torpor has to rely entirely on the spacecraft's pre-positioned shielding and autonomous monitoring to manage a particle event, because no human is awake to make a decision, adjust behavior, or reposition within the vehicle. The solar particle event management problem has a practical dimension worth naming. On the International Space Station, flight controllers monitor the sun continuously, and an alert goes to the crew when an event is detected so they can shelter in the most shielded module. The crew moves and adjusts position based on human judgment and real-time ground communication. A torpor mission has no crew available to receive that alert and respond. The spacecraft's autonomous systems would have to detect the event, assess its severity, and either determine that the fixed shielding is adequate or initiate a wake-up protocol if the event exceeds shielding capacity. That wake-up protocol carries its own medical risks and would interrupt the planned torpor phase. The alternative, accepting whatever dose the shielding geometry provides during an unplanned solar event, is a risk that mission planners would have to quantify and accept in advance. The radiation picture is not uniformly pessimistic. The concentrated shielding geometry is a real advantage, and the possible biological radioresistance in torpor is a genuine hypothesis with animal evidence behind it. Better shielding materials currently under development, including hydrogen-rich polymer composites and liquid hydrogen as dual-function fuel and shielding, could improve the picture further, but these are future possibilities superimposed on a current reality. Deep space radiation is a chronic hazard that does not respond to whether the crew is conscious of it, and the chronic component of that hazard has not been demonstrated to be meaningfully reduced by any torpor state in any human subject. Radiation is not the only thing that keeps working while the crew is motionless. Think about what astronauts on the International Space Station do without exception. Every single day they are aboard. They exercise, not to stay fit in the ordinary recreational sense, but because if they do not, the human body in weightlessness begins methodically dismantling itself. Muscle mass falls, bone density drops, fluid redistributes toward the head, cardiovascular efficiency declines. The body is doing what evolution shaped it to do in the absence of the gravitational loading it was built for. It adapts to a world where that mass and that strength are no longer needed. The countermeasure is structured, mandatory, and time-consuming. Station crew members typically spend around 2 hours a day on resistance exercise and cardiovascular work, specifically to slow the rate of these changes. After 6 months on the station, returning astronauts still need weeks of rehabilitation to walk without assistance, rebuild strength and coordination, and restore cardiovascular function adequate for normal activity. The exercise regime helps significantly, but it does not eliminate the effects of extended weightlessness. It manages them enough to allow safe return and recovery. Now take away the exercise. A crew in torpor pods cannot do their daily countermeasure routine. They cannot load their bones with mechanical stress. They cannot contract muscles against resistance. They float in a fixed position, largely immobile, for the duration of the cruise. The question this raises is whether the metabolic and physiological state of torpor changes how the body responds to that situation. And the honest answer is that the available evidence does not resolve this question for humans. The ESA architecture study includes an expectation drawn from animal hibernation research. Crew members in torpor might not experience the degree of bone and muscle deterioration that would otherwise accumulate over a 180-day cruise. Hibernating animals provide the reference. Some species emerge from months-long hibernation with muscle mass and bone density largely intact, despite being mostly immobile throughout the season. If that biology translated to a human crew in managed torpor, the absence of daily exercise countermeasures might not produce the expected deterioration, or might produce it more slowly. ESA frames this carefully as an expectation from animal evidence, not as a demonstrated human outcome. The gap between those two things is significant and has to be named plainly. The animals that preserve muscle and bone during hibernation do so through an active biological program of coordinated metabolic and hormonal changes that their bodies evolved to run during torpor. Human beings did not evolve to hibernate. Whether the same protective mechanisms can be triggered in humans, and whether they would operate under the specific conditions of microgravity during a pharmacologically managed torpor state, is not established by any human clinical data. It is a biological aspiration worth investigating, grounded in genuine animal evidence, but not yet demonstrated in the system it is assumed for. The microgravity problem extends beyond muscle and bone. Weightlessness drives fluid redistribution toward the head and upper body, which can elevate intracranial and intraocular pressure. This is associated with what researchers call spaceflight-associated neuroocular syndrome, a condition in which the structures of the eye and optic nerve are altered by the chronic pressure changes of microgravity exposure, sometimes producing measurable changes in visual acuity that persist after return to Earth. Some astronauts on long-duration missions have returned with meaningful changes to their vision that were not present at launch. Whether a torpor state modifies the fluid dynamics that drive this effect is unknown. Cardiovascular function adapts to the absence of hydrostatic pressure in the lower body. In normal Earth gravity, the heart works continuously to pump blood upward against gravity. In weightlessness, this workload is absent, and the cardiovascular system responds by reducing its capacity for that work. The changes compound over months. A crew in torpor experiences this same gravitational absence for the same duration. Whether metabolic suppression changes how the cardiovascular system adapts to weightlessness has not been tested in any human study. Kidney function changes in microgravity, including alterations in calcium handling that interact with the bone density changes. The immune system operates differently in weightlessness, with changes in immune cell profiles and reactivation of latent viruses being documented in long-duration mission crews. These effects do not pause because the crew member is in a reduced metabolic state. Gravity is still absent. Fluid redistribution still occurs. The physiological environment of weightlessness keeps acting on every system in the body simultaneously. For an active crew, the exercise countermeasure provides some of the mechanical and cardiovascular stimulus that would otherwise come from living in gravity. It is an imperfect substitute, but a meaningful one. A crew in torpor has none of that substitute. If the torpor state itself provides some protective effect, as the animal biology suggests is at least plausible, the absence of the countermeasure might be partially offset by that biology. If it does not, dormancy may worsen deconditioning compared with an active crew doing their daily exercise. This is why ESA's expectation is framed as an expectation and not a claim. The animal evidence is real. The gap between the animal evidence and demonstrated human microgravity torpor protection is also real. Holding both simultaneously is the honest position. The body in a torpor pod is not inert. It is a living system being continuously modified by its environment. Weightlessness keeps working on it regardless of its metabolic state. The fluid shifts happen, the cardiovascular system adapts, the bones and muscles respond to the mechanical environment they are in. Whether the biology of torpor protects against any of these responses in a human under spaceflight conditions is the open question. The interaction between torpor and microgravity also cuts in a direction worth noting separately from the muscle and bone question. Astronauts on long-duration missions experience changes in spinal length. The discs expand without the compression of gravity, producing a measurable height increase that reverses on return to Earth, but can cause discomfort and is associated with increased risk of herniation. The cardiovascular system adapts to the absence of the hydrostatic pressure that normally exists from standing. The vestibular system, the body's sense of balance and orientation, adapts to the absence of gravity cues in a way that requires recalibration when the crew returns to a gravity environment. None of these adaptations pause because the person is in a reduced metabolic state. The gravitational environment is unchanged regardless of metabolic rate. What the torpor concept is asking is whether a metabolic and physiological state that evolved as an energy conservation strategy in seasonally fasting animals also happens to provide protection against the specific adaptations that weightlessness drives in the human body. The answer might be yes, partially, for some systems. It might be no for others. The animal evidence is genuine enough to make the question worth asking carefully. It is not sufficient to assume the answer without testing it. The honest position keeps both possibilities open without collapsing to either conclusion in advance of evidence. ESA's expectation that bone and muscle wastage might be reduced is not a dismissed hope. It is a grounded biological possibility that requires human microgravity torpor data to confirm or correct. Until that data exists, the expectation remains what ESA called it, an expectation. To protect a motionless body through months of weightlessness, the pod has to become a medical system. Look at the pod not as a sleeping chamber, but as a piece of medical equipment. The tubes running in and out carry nutrition, remove waste, and provide continuous chemical sampling. Thermal management holds core temperature steady as the spacecraft moves through the solar system. Sensors along the frame track cardiac rhythm and detect early tissue damage from immobility. Software watches all of it simultaneously and has to make decisions without asking anyone. The occupant is alive, but cannot help. The pod is not a bed, it is an automated intensive care room, and that distinction changes what kind of engineering problem it represents. The medical requirements that a torpor pod has to satisfy begin with nutrition. A body in reduced metabolic state still needs energy and nutrients, though the caloric requirement is substantially lower than normal, perhaps 30 to 50% lower. The gut slows during deep inactivity, making normal eating impossible, and some form of enteral or parenteral feeding becomes necessary with precise dosing maintained over months. Waste is an equally practical problem. Digestion does not stop. Kidneys continue to filter blood and produce urine. A human in a torpor pod still produces waste that has to be managed without any cooperation from the occupant. Urinary catheterization becomes standard. Digestive waste requires management through some combination of dietary design and mechanical collection. In a hospital, both are handled routinely by nursing staff, who can intervene immediately if a problem develops. In a spacecraft, they have to be handled by automated systems that must operate reliably for 6 months without maintenance, without sensor drift going uncorrected, and without human oversight. Blood clots are a risk that intensifies with immobility. When muscles are not contracting normally, the pumping action that moves blood through the deep veins of the legs and pelvis is absent or reduced. Blood can pool. Deep vein thrombosis can form, with the risk of a clot traveling to the lungs and causing a pulmonary embolism. In an active astronaut, movement and exercise provide the mechanical stimulation that helps prevent this. In a torpor pod, that stimulation is absent. Pharmacological anticoagulation could reduce the risk, but it carries its own complications, including increased bleeding risk if any injury occurs. Mechanical leg compression devices might help, but they require power and long-term mechanical reliability. Pressure injuries are a related concern. A human lying in the same position for hours develops pressure damage to the skin and underlying tissue at contact points. In a hospital, patients are repositioned on a regular schedule to prevent this. In a torpor pod, repositioning would require mechanical systems capable of moving a human body through a limited range of positions without waking the occupant and without causing injury. For an overnight hospital stay, this would be straightforward. For a 180-day cruise, it becomes a reliability and design requirement of significant complexity. Infection risk is continuous throughout dormancy. The body in a reduced immune state is more susceptible to microbial challenge. The closed environment of a spacecraft is not sterile and cannot be made fully sterile over a long mission duration. Bacteria persist on surfaces and in air handling systems. Fungi can establish themselves in confined, humid environments. A crew member who would normally clear a minor infection through active immune response may not mount that response normally in a suppressed metabolic state. Monitoring for early signs of infection, changes in temperature and biochemical indicators requires sensors that work continuously and decision logic that can respond appropriately when an alarm fires. Temperature regulation requires continuous active management throughout the cruise. Torpor depends on maintaining a specific core temperature range. Too cold and the dangerous hypothermia thresholds that clinical medicine describes become relevant. Cardiac arrhythmias, electrolyte destabilization, and organ stress. Too warm and the metabolic suppression becomes insufficient. The crew member may begin to arouse from the torpor state, and the pharmacological management has to adjust. The pod's thermal system has to track both core temperature and the spacecraft's external thermal environment, and adjust continuously over months without component failure. Electrolytes, sodium and potassium in particular, shift during prolonged inactivity and during metabolic suppression. Their balance affects cardiac rhythm, nerve function, and cell membrane stability. Monitoring them requires some form of continuous or frequent chemical sensing that can operate without access to a full medical laboratory. Managing them requires automated adjustment of the fluids and nutrients being delivered based on sensor readings that may themselves have drift or calibration issues after months of operation. The rewarming process at the end of the cruise adds another phase of medical complexity. The body's chemistry reactivates unevenly as temperature rises. Cardiovascular rhythm requires monitoring as temperature rises, while immune, hormonal, and digestive function all reactivate in sequence. A crew member waking from a 180-day torpor is not stepping out of a cabin refreshed. ESA's architecture study includes a 21-day recuperation period after the cruise, which makes the point plainly: recovery is a mission phase, not a moment or a movie cut. What all of this amounts to is an automated medical system operating continuously for months, surviving radiation and the general stress of a deep space mission without maintenance and without the ability to call a specialist. The spacecraft becomes the doctor, the pharmacist, and the laboratory all at once. The engineering challenge extends into what might seem like mundane details but are not. Every sensor in the pod has to function after months in a radiation environment. Sensors drift. Calibration changes over time. A temperature reading that was accurate at launch may be systematically off by 1/10 of a degree after 4 months of accumulated radiation damage, and for a system managing a narrow temperature range, 1/10 of a degree matters. The software managing the monitoring has to be capable of detecting its own calibration drift, or the hardware has to provide redundant sensors that can cross-check each other. Both solutions add mass, complexity, and potential failure modes. Power is a continuous requirement throughout the cruise. Every sensor, thermal system, and fluid pump has to run on the spacecraft's power budget for the full duration of the torpor phase. Power systems can degrade. Solar panels deliver less power at Mars distance than at Earth distance. Battery storage has to bridge any shortfalls. If power management fails and a pod loses thermal control, the crew member inside is at risk. The pod's power budget has to be treated with the same criticality as a life support system, because that is what it is. Communication with the pods, transmitting data from sensors to the spacecraft's central monitoring system and back, has to be reliable and secure against the kind of electromagnetic environment that a spacecraft generates. A pod that fails to transmit a sensor reading is indistinguishable, from the central monitoring system's perspective, from a pod where the sensor itself failed. The system has to distinguish between communication loss and actual sensor loss, and respond correctly to each. If every crew member is simultaneously a patient requiring continuous medical management, the spacecraft itself has to become the active crew member. The alert light blinks in an empty section of the spacecraft. An internal sensor has flagged something, a pressure differential in a fluid line, a thermal reading that has moved outside its expected range, a vibration pattern that does not match the baseline established during commissioning. In a conventional mission, a crew member would be nearby. They would walk over, check the display against their training, and make a judgment call about whether the reading represents a sensor anomaly or a real problem. The spacecraft continues because a human was available to assess and respond. In the torpor architecture, no one is nearby. The crew is in the pods. The spacecraft has to handle this on its own. That shift from a crew managing a spacecraft to a spacecraft managing itself is one of the most significant and least discussed costs of the torpor concept. It does not appear in the habitat mass budget. It does not reduce consumables or shrink the living volume, but it represents a fundamental change in how the mission works, and it places demands on spacecraft autonomy that current deep space systems have not been designed to meet. ESA's architecture study is explicit about this. The spacecraft needs largely autonomous fault detection and recovery, determining what went wrong and tracing it to the source without human direction. Such fault management capabilities are well developed for specific, anticipated failures, but far more difficult to guarantee across the full range of possible anomalies on a complex, crewed deep space vehicle over a 6-month mission. The fundamental problem with autonomous fault management is the space of possible failures. A crewed deep space spacecraft has thousands of interdependent components whose failures can interact in non-obvious ways. Some modes are well characterized and handled by pre-programmed responses, but novel cascading failures that no test scenario anticipated fall outside that envelope. Where a crew member can observe and adapt, automated systems can only execute the designs they were given. When a situation falls outside the design envelope, they fail in ways that are sometimes not detectable and sometimes not recoverable. The communication distance compounds the autonomy problem. At Mars distances, a one-way radio signal takes between 3 and 22 minutes depending on orbital positions, making a round-trip exchange 6 minutes at minimum and potentially over 40. Ground controllers cannot provide real-time guidance for any anomaly that develops during the cruise. By the time a description of the problem reaches Earth and a response returns, the spacecraft has already had to handle the situation with whatever automated logic was aboard at launch. This communication delay is a feature of any Mars mission, not uniquely a torpor problem. But in a conventional crewed mission, the crew handles real-time decisions themselves. Ground control is a backup resource, not the primary decision-making authority for anomalies that require immediate response. In a torpor mission, that real-time human judgment is absent, and every decision that would be made by a crew member has to be made by the spacecraft's automated systems or deferred until the crew can be woken, which is itself a medical event with its own timeline and risks. Medical emergencies within the pods add another layer. A crew member developing a serious complication during torpor, whether a cardiac arrhythmia or a clotting event, requires a response that in a clinical setting would involve humans making continuous assessments. In the torpor spacecraft, automated diagnostic and intervention systems have to both identify the complication and determine whether the crew member should be woken early. Early waking carries its own complications. The recuperation period exists because the body needs time to safely transition from torpor to full function, and a crew member woken mid-cruise may face reduced physical and cognitive capability at exactly the moment the spacecraft needs them. Rewarming outside the planned schedule and outside the full recuperation window is not a neutral act. The autonomy required for a torpor mission is a category of ongoing requirements, not a single engineering problem to solve once. Managing spacecraft systems and crew medical conditions falls to automated systems simultaneously with all the trajectory and environmental monitoring that normally occupies active crew attention, but without anyone available to handle any of it. The concept that seems simpler turns out to require a more sophisticated spacecraft, not a less sophisticated one. A conventional active crew manages many problems themselves, which reduces the autonomy requirement on the spacecraft systems. A torpor mission transfers that entire management burden to automated systems that have to be substantially more capable, more reliable, and more robustly tested than anything currently flying on crewed deep space missions. The category of failures that concerns mission planners most is not the anticipated ones, but the unanticipated ones. Pre-programmed fault responses handle scenarios that engineers modeled before launch. The harder cases involve unanticipated interactions. A sensor fault changes how the spacecraft reads a downstream system, and the automated response to that reading causes a third problem to worsen. A human watching the same displays would recognize something wrong in the overall pattern. Automated systems that compare values to thresholds cannot make that judgment when the pattern is genuinely novel. Advancing toward that reasoning capability is one of the engineering frontiers that a torpor mission would force open. Systems capable of reasoning about internal spacecraft state, rather than only flagging threshold violations, would represent a meaningful advance in deep space autonomy. The communication constraint makes this especially important because the spacecraft cannot defer to ground controllers on any useful timescale. For a torpor mission specifically, there is no crew available to serve as the adaptive judgment layer that conventional missions rely on. The autonomous system has to cover judgment that would normally be shared between crew and vehicle systems, without any human fallback available. The same study that projects mass savings also specifies that largely autonomous operations would be required, and the two findings are inseparable. The smaller spacecraft is only possible if the more capable autonomous system is already present. Framing the autonomy requirement as a design specification rather than a barrier clarifies the challenge. Spacecraft autonomy has been advancing steadily, with deep space probes already executing complex orbital maneuvers autonomously and autonomous landing systems having guided spacecraft to Mars without real-time ground oversight. The gap between current autonomy capability and what a torpor mission requires is real, but also a defined engineering target with identifiable requirements that can be translated into development work. The difference between a conventional Mars mission and a torpor Mars mission, from the autonomy perspective, is primarily a question of what the spacecraft has to handle alone versus what the crew handles as partners. Every capability that the spacecraft develops for autonomous operation in the torpor scenario is also a capability that makes the spacecraft more capable in a conventional mission, better at handling anomalies when crew attention is focused elsewhere, and better at responding to contingencies before the ground can weigh in. The autonomy investment for torpor has spillover value across the broader mission architecture. The Mars-class framing remains important here. The cruise phase is months, and the communication delays are minutes to hours. Stretching these parameters toward the outer solar system changes the autonomy requirements in ways the Mars architecture study was not designed to address. Lay the mission durations side by side. On one end, a Mars transfer, roughly 6 to 9 months one way under current mission planning, with the ESA study's assumed 180-day torpor cruise as the specific architectural reference. Move outward across the solar system and the timescales change their character entirely. A mission to Jupiter using realistic near-term propulsion takes roughly 2 to 3 years one way. Saturn adds another year or two. Voyager 2 launched in 1977 and reached Neptune in 1989, a 12-year crossing at speeds no crewed mission to date has matched, and that spacecraft was on a gravity-assist trajectory optimized for speed, not breaking into orbit. A crewed mission to the outer planets, decelerating to enter orbit, would involve durations of a different scale entirely. The Mars architecture study lives at the near end of that range. The 180-day torpor cruise is the specific scenario that ESA modeled, that SpaceWorks designed a habitat around, and that the most concrete and carefully examined mission planning numbers describe. It is not a conceptual placeholder. It is the specific case where the evidence for the concept is strongest and where the engineering trade-offs have been worked through in the most detail. That specificity matters because torpor concepts do not automatically scale to longer durations. What changes as the trip gets longer follows a clear pattern. A 6-month torpor state is already at the outer edge of anything that clinical medicine or animal biology suggests is tractable for human management. The metabolic effects of suppression compound over time. Drug pharmacokinetics shift over months as the body's processing changes during extended dormancy. Medical risks accumulate. The probability that some complication will occur grows with every additional week. System reliability requirements grow more demanding because a component with a 1% chance of failing over 6 months has a much higher probability of failing over 6 years. Radiation dose accumulates linearly with exposure time. The autonomous operations requirement on the spacecraft intensifies with duration because there are more opportunities for unanticipated situations and more time during which the crew cannot contribute to resolving them. Extend the mission to the outer planets, and these challenges multiply without the supporting evidence growing proportionally. No animal species is known to hibernate for 3 years continuously. There is no clinical data on human metabolic suppression safely maintained over a year. There is no spacecraft autonomy system validated for a decade of continuous crewed life support without human oversight or the ability to schedule maintenance. The Mars architecture study's specific assumptions, 180 days of torpor in a pharmacologically managed state with automated monitoring, were designed for that particular mission profile and cannot simply be stretched toward Jupiter without confronting gaps the study was not designed to address. The outer solar system also changes the communication problem in a way that qualitatively shifts the autonomy requirement. At Mars distances, a radio signal takes between 3 and 22 minutes one way. At Jupiter's average distance, the one-way delay is approximately 30 to 45 minutes. At Saturn, it rises to over an hour. At Uranus and Neptune, the delay is 2 to 3 hours each way. Ground controllers cannot intervene in any timely way for anomalies at those distances. The spacecraft at the outer planets is not operating with delayed communication. It is operating essentially alone, with ground control capable only of historical review of what happened, not real-time assistance with what is happening. For a torpor mission at outer planet distances, this is the condition under which automated systems have to manage 6 sleeping crew members for years, not months, years. Reliability requirements on all monitoring systems, medical devices and software processes become correspondingly more severe. A system with a mean time between failures suitable for a 6-month cruise may be entirely inadequate for a 6-year mission to Jupiter-class distances. The century-scale case is categorically different again. Generation ship scenarios, hypothetical journeys to the far outer solar system, or speculative interstellar adjacent concepts. These scenarios require dormancy durations that have no biological or medical reference point. A person sleeping for a century is not a person in an extended version of a 6-month torpor state. It is a biological proposition with no demonstrated mechanism, no known precedent in any mammalian species, and no framework for understanding what the body and mind would require during or after such a period. The systems required to keep a human being alive and recoverable for a century of deep space dormancy are not a more sophisticated version of a Mars transfer habitat. They represent a fundamentally different and currently imaginary category of engineering and biology. Duration categories matter and have to be kept distinct. Mars transfer torpor concepts are Mars transfer concepts. They represent a specific range of mission duration, months, for which the motivating evidence is relatively strong and the engineering has been examined in useful detail. They do not automatically validate the idea for outer planet missions measured in years, and they do not validate anything at the speculative century-scale boundary. The honest version of the torpor concept gains its credibility precisely from this modesty. The Mars architecture studies work because they are grounded in a specific mission profile, specific duration assumptions, and specific engineering trade-offs. The moment those assumptions are stretched toward the outer solar system, the supporting evidence thins and the extrapolation becomes speculative. At the far reaches of the solar system, the concept becomes less a mission architecture study and more a question about whether the fundamental limits of human biology could eventually be extended in that direction. The picture so far is clear enough to hold in mind. The pod at the beginning of this journey was about mass, medicine, and the monitoring requirement. A picture has formed. Torpor architecture may make a Mars-class transfer more practical in specific, quantifiable ways, while leaving several major biological and engineering problems unresolved. That picture holds for the scenario the research was designed to address. A qualitative change in what the biology has to accomplish separates the 6-month torpor from anything measured in years. For a 6-month torpor, the challenge is primarily physiological, keeping the body stable through a defined period of suppressed metabolism while the spacecraft crosses a known distance. For a multi-year outer planet torpor, the challenge begins to include biological time at a scale where human physiology has no precedent. Cells age, DNA accumulates damage from radiation exposure over years. Hormonal systems may drift in unpredictable ways over multi-year suppression periods. The immune system changes character over time. What a human body looks like after 3 years of managed metabolic suppression in space is genuinely unknown because no one has studied anything close to it. For a century-scale torpor scenario, the biological time question becomes the central problem rather than a secondary concern. A century is not a long time from the perspective of deep space. It is a short portion of the time it would take to reach any other star system, and it is comparable to the human lifespan itself. A person who entered a century-long torpor at age 30 would emerge, if they emerged at all, at what should be age 30, but into a century that has passed. The biological meaning of that is not described anywhere in medicine because the scenario is so far outside any reference frame that current biology can offer. Now the question extends to the far edge. At the far edge, hibernation becomes less a Mars tool and more a question about skipping a lifetime. Imagine the pod not at the 6-month mark of a Mars transfer, but much later. The spacecraft is old. Its seals and filters have accumulated thousands of thermal cycles and years of wear without maintenance stops. And its software has run for years without a human reviewing the error logs or approving updates. The radiation shielding is still positioned around the pods, but galactic cosmic rays have been passing through the hull for a decade or 2 or longer. Inside the pod, one body has been there the whole time, suspended in a state that no biology textbook describes for a human. The century-scale boundary is a different scientific category from anything that the Mars architecture studies address. The Mars transfer concept works with specific assumptions. 6 months of torpor in a pharmacologically managed state, with automated monitoring and a recuperation period at the end. That concept has a basis in clinical medicine, animal biology, and engineering analysis. It is not proven, but it is grounded in real numbers and real reference points. When ESA projects a 1/3 reduction in spacecraft mass, or SpaceWorks proposes a 5 to 7 metric ton habitat, those figures connect to specific mission parameters that can be examined and challenged. Extend that same concept to decades or a century, and every one of those reference points disappears. No mammal is known to hibernate continuously for more than a few months without arousal. The longest natural torpor bouts in hibernating species last weeks, not years. Hibernation in the animals that practice it is a cyclic, managed strategy that depends on periodic arousals, the body waking briefly to assess its condition and adjust its chemistry before returning to dormancy. The biological stability of hibernation over a full season comes from that cycling, not from a single unbroken suspension. The animal is actively managing its state, not simply frozen in place. A human torpor mission of decades or centuries would not be an extended version of that natural strategy. It would be something for which no biological model exists. The radiation dose at the century scale becomes a problem of a completely different order. A 6-month Mars transfer accumulates a radiation dose that is already above what astronauts receive during comparable time on the International Space Station. Extend that exposure to a decade, and the cumulative dose crosses thresholds associated with substantially elevated cancer risk under current radiation medicine models. Extend it to a century, and the total galactic cosmic ray dose alone, even with the best shielding that practical spacecraft engineering can provide, would exceed any biological limit that current understanding recognizes as compatible with survival. Hibernation radio resistance evidence from animal studies, even if it translated fully to humans, which no evidence currently supports, would not change the arithmetic of a century of chronic irradiation. The mathematics of dose are not biological preferences, they are physics. The contrast with the 6-month Mars case illustrates how qualitatively different the century scenario is. At Mars distances and on a 6-month transfer timeline, the physics and biology define a hard but investigable set of problems. Each problem has an analog in current research or clinical medicine, and each can be mapped to a specific research direction with identifiable requirements. At the century scale, the problems no longer have analogues. They are outside the envelope of any investigation currently underway, and no extrapolation from Mars-class evidence closes the distance between them. System reliability is another dimension that changes character entirely at long timescales. A life support monitoring system built for a 6-month cruise can be designed with redundancies and safety margins that give it high confidence of surviving that duration. The same system running for a century faces a fundamentally different challenge. Mean time between failures becomes the governing constraint. Components degrade, elastomers harden and crack, and software accumulates bit flip errors from radiation that cannot be corrected without human oversight. The reliability architecture required for a century is categorically different from what a Mars transfer design assumes. Data integrity is a related concern that rarely receives attention in popular discussions. The computer systems managing a torpor mission maintain models of the crew's medical status and the spacecraft's operational trajectory. Over a century, the radiation environment in deep space can corrupt memory and logic systems in ways that accumulate gradually and may not be detectable through automated checks. Software that was correctly verified at launch may encounter edge cases or bit corruption events that produce subtly wrong outputs for years before failing obviously. Redundancy helps, but redundancy built for a 6-month mission is not automatically adequate for a century. Beyond the biology and engineering, the crew also wakes into an unfamiliar future. At the end of a Mars transfer, the crew recovers over a few weeks and enters a mission for which they have prepared and trained. At the end of a century in transit, assuming the body survived and the recovery was successful, the crew would be waking in a future they have not experienced. The social, technological, and mission context they trained for would be a century stale. Their skills would be shaped for conditions that no longer apply, and no medical or experiential reference point exists for a person emerging from a century of dormancy into the operational demands of a spacecraft near an unfamiliar destination. The century boundary matters because it tends to appear in public discussions as though it was simply an extension of the Mars torpor concept. The word hibernation is the same and the pod image is similar, but the underlying scientific claim is entirely different. The Mars concept is grounded in studies and clinical analogues that justify serious investigation, while the century scenario is a thought experiment at the outer edge of what biology might eventually address, not a claim that present science validates. The honest answer at this boundary is to name the distinction clearly and hold it. The possibility that biology and engineering might eventually extend the capability toward longer durations is not absurd. The history of technology contains many such examples. But the possibility is not the same as the claim. Preserving the possibility means acknowledging the uncertainty and not presenting a future scenario as though current research has already closed the distance to it. The century boundary also raises a question of purpose and meaning. A person entering a century-long torpor is removing themselves from the timeline of human events. A century will have passed when they wake. The civilization that sent them will have changed its direction, and the people they knew will be gone. Exploration has always involved the possibility of no return, and some of the most significant human crossings have been one way in practical terms. But the century boundary adds a dimension that purely biological or engineering arguments do not capture. The person waking from a century of dormancy near a distant destination is not returning to anything familiar. They are beginning something entirely new in a context they cannot have prepared for. That dimension does not change the physics or the biology, but it is part of the honest picture of what century-scale deep space torpor would actually mean for the people inside the pods. The honest answer has to preserve the possibility without selling the fantasy. Look at the Mars transfer habitat again, but this time with the full picture of what has been established and what has not. The pods are smaller than a conventional crew cabin, the mass budget is lighter, the shielding geometry concentrates protection around the crew, and the number of active person days in the cruise phase drops dramatically. On paper, those savings are real, and the architectural incentive to pursue the concept is genuine. But surrounding that picture is everything that still needs to work: autonomous medical monitoring for 6 months, and the unresolved biological and engineering requirements that the architecture studies quantify but do not solve. The habitat gets smaller while the problem around it remains large. The question worth staying with is not whether the torpor concept could theoretically advance. It is what the strongest realistic version of the concept actually delivers, and what it does not. The strongest near-term value is not making impossible journeys suddenly possible. It is making the transfer phase of a specific, achievable mission, a Mars-class transfer, more practical than it would be under conventional design assumptions. Those are very different outcomes, and keeping the distinction clear is part of what makes the evidence honest. A mission to Mars is already within the engineering horizon of near-term human spaceflight. Propulsion and trajectory are well understood for Mars missions, and the distance is manageable by the difficult standards of deep space travel. The challenge is the mass budget, the consumables, and the psychological burden of months of confinement in a small, closed environment on a crew that needs to arrive functional. Torpor architecture, if it could be demonstrated to work safely, addresses several of those problems simultaneously in a way that other approaches struggle to match. ESA's projection that a hibernating crew might allow roughly 1/3 reduction in spacecraft mass would change the cost structure of a Mars mission in concrete ways. Smaller habitats reduce structural mass, lower consumables shrink the logistics chain, and a crew arriving with less confinement stress may perform better during the mission phases that matter most. These are real benefits in the context of a mission that is genuinely difficult to execute under conventional assumptions. They are not marginal improvements. The SpaceWorks numbers make the trade concrete. A torpor transfer habitat at 5 to 7 metric tons, with around 20 cubic meters of volume for 4 to 6 crew, compared with 20 to 50 metric tons and roughly 200 cubic meters in conventional designs. That difference is not aesthetic. It changes the mass delivered to Mars orbit, the propellant required for orbit insertion, and the downstream architecture of everything that follows the transfer phase. What the concept does not deliver is an escape from the biological cost of the journey. Radiation exposure accumulates regardless of consciousness, and microgravity acts on the body regardless of metabolic rate, unless the torpor state itself provides protective effects that no human data currently demonstrates. The medical monitoring burden requires autonomous systems that add their own complexity, and the wake-up recovery adds 3 or more weeks before the crew is operationally ready. The bounded verdict is important precisely because both failure modes, overselling and underselling, carry real costs. Overselling torpor technology as operational cryosleep sets expectations that the research cannot meet, and potentially misleads mission planners who treat speculative concepts as readiness thresholds. Underselling it by dismissing the architectural benefits because the biology is unresolved ignores real evidence that a serious, productive research direction exists. The architecture benefits are genuine and substantial under the study assumptions. while the biological requirements that would make them real are genuine and currently unresolved, and the honest position holds both simultaneously without collapsing into either easy conclusion. Each unsolved component has a research direction. Induction pharmacology draws on existing work in clinical sedation, metabolic regulation, and the synthetic torpor research in animal models, while autonomous medical monitoring draws on intensive care miniaturization and closed-loop medical device design. Microgravity protection draws on the hibernation biology literature and whatever human torpor analog studies can eventually be conducted, along with recovery protocols informed by clinical hypothermia and long-duration sedation outcomes. None of these pathways is trivially short, but none of them is obviously closed. The concept is also not in isolation. Each advance in any of these directions makes the combined system more feasible, and research in any of these areas for other purposes can contribute to the torpor mission architecture indirectly. A useful tool with strict boundaries is still a useful tool. A Mars transfer that costs 1/3 less mass, requires fewer active person days, and delivers a crew with less accumulated confinement burden is a meaningfully different mission from one that does not. Whether the torpor concept can eventually deliver those benefits safely is the research question. The architectural case for trying to answer it is established. The comparison baseline matters for assessing the value correctly. A conventional Mars transfer requires all crew to remain functional throughout the cruise, with adequate provisions, regular exercise, and a psychological environment designed to prevent deterioration over months in a small, closed environment. The cumulative cost of that maintenance, in mass and in daily human effort, is already a known problem for mission designers. Torpor architecture does not only add a capability, it removes a cost that would otherwise have to be paid in some form, whether by launching more mass or accepting crew degradation before Mars surface operations begin. That framing changes the comparison. Torpor's architectural case rests not on its value in isolation, but on whether it reduces total mission cost relative to the conventional design, accounting for the complexity of autonomous medical management. Favorable results in that comparison is what the engineering studies suggest is achievable, and that is why the architectural case for resolving the biology is established. The research pathway also has a useful asymmetry. Progress in any one component has value that extends beyond the torpor mission concept itself. Advances in autonomous medical monitoring developed for a torpor habitat would improve intensive care in remote settings, while better pharmacological tools could carry over into terrestrial medicine. Better spacecraft autonomy further makes all deep space missions safer by reducing dependence on crew availability. The torpor concept sits at the intersection of several research directions that are individually worth pursuing and collectively necessary for the space application. The timing of the concept also has a practical dimension. The architectural benefits are clearest for missions that are already within the near-term engineering horizon, Mars-class transfers, in the time frame when human Mars missions are actually being planned and designed. That timing is relevant because it means the research has a defined application to aim at, something more grounded than an abstract future mission. If the biology and engineering can be advanced enough to support a Mars-class torpor architecture in the relevant planning window, the benefits are available for actual missions. If development continues past that window, the benefits extend to subsequent missions with the same or longer transfer phases. That is a specific and actionable research target, not a promise that everything will work, and not a dismissal that nothing is achievable. A defined architectural goal with a real mission application, a clear set of required capabilities, and research directions that can be pursued with existing scientific and engineering tools. A useful tool still needs biology, medicine, and autonomy to succeed together. Picture a checklist on the wall beside the pod. Safely induce a torpor-like state in a healthy human adult, maintain it for 6 months through monitored medical management, and reverse it safely within the recuperation timeline. Each item, examined alone, has a research pathway. As a combined requirement, the list presents a different challenge. Every single item has to succeed simultaneously in the same spacecraft over the same 6-month cruise, with no option to pause the mission and retry a component that failed. The central research gap is integrated success. The animal evidence and the architectural studies have established that torpor is worth pursuing, and medicine and biology have made real progress on individual pieces. What remains unresolved is all of the required capabilities working together reliably in the specific and unforgiving conditions of deep space flight. Start with induction. Pharmacologically inducing a torpor-like state in a healthy human adult is not the same as sedating someone for a surgical procedure. Surgical sedation is titrated to a specific depth for a specific short duration, with an anesthesiologist continuously monitoring and adjusting agents, and the patient recovering over hours. Torpor induction for a 6-month cruise would need to suppress metabolism significantly and durably, using pharmacological agents whose long-term effects in a healthy person, not a patient with an underlying injury, have not been described in any clinical literature. The agents would be administered over months, and their metabolism would shift as the body changes during extended dormancy. So dosing appropriate at month 1 may not be appropriate at month 3. The entire induction and maintenance pharmacology has to be managed by automated systems that have no clinical precedent to follow. Clinical cooling, which confirms that human metabolism can be reduced under intensive medical care, is the nearest human analog. But clinical cooling is a short-duration intervention managed by a trained team with access to the patient. The leap to autonomous pharmacological torpor induction for a crew in deep space, sustained over months, is a substantial one with no established bridge. Maintenance is the next item and arguably the most complex. Once a torpor state is induced and stable, keeping it there over 6 months requires managing temperature within a narrow functional range, preventing blood clotting and fluid imbalance, and keeping all the associated hardware operating correctly without maintenance access. Each of these requirements has been described in the Pod Is ICU context. Together they describe an automated medical system of extraordinary sophistication that has to run without staff, without the ability to request help, and without any human oversight for the duration. The monitoring challenge has 2 dimensions: reliable physiological sensing over months in a radiation environment, and autonomous clinical decision-making without the trained human judgment that medicine currently requires for these decisions. Building that judgment into an automated system for the full range of possible events across 6 patients is a problem that intensive care medicine and autonomous systems engineering have not yet solved together. The interactions between required capabilities add another layer of difficulty. Microgravity affects fluid distribution and cardiovascular monitoring baselines. Immune suppression from metabolic suppression shifts infection thresholds. Pharmacological torpor agents interact with anticoagulation agents, which interact with the monitored cardiac signals that guide dosing decisions. These are predictable intersections of physiological systems that all have to operate correctly in the same body simultaneously. The translation from animal biology to human mission capability is where the integrated challenge becomes most visible. Natural hibernation works because evolution solved the integration problem across millions of years. The hibernating animal runs the complete program from induction through maintenance to arousal, entirely from within its own biology, with every system coordinated by the same evolved machinery and no external pharmacology needed. The animal's body is the integrated solution. A human torpor mission would have to solve the integration problem through medicine and engineering in a system not designed by evolution for this purpose, and on a timeline determined by mission planning rather than seasonal biology. The components each exist as a separate research direction that has made genuine progress, but the integration of all of them into a demonstrated and reliable autonomous system has not yet been achieved. Recovery adds the final item. After a 6-month torpor cruise, the crew wakes into the medical process described in the recuperation period. Rewarming has to be managed while metabolic systems reactivate and both muscle and cognitive function return gradually. The crew has to be evaluated for complications before mission-critical work begins. If induction was incomplete, if maintenance produced a complication, or if recovery does not restore function within the planned timeline, the mission is affected in ways that cannot simply be rerun. The biological and engineering pieces exist, and each has a research direction that has made genuine progress. What does not yet exist is the demonstration that they work together reliably in the same system under the right conditions. Defining what counts as success adds another layer to the problem. An integration that works 95% of the time in terrestrial testing might still carry meaningful risk over a 6-month autonomous mission with 6 patients and no ability to intervene from outside. The reliability standards that define an acceptable autonomous medical system for a deep space torpor mission are not the same as the standards for a clinical device used under regular staff supervision. Failures that are manageable in a hospital because staff are present and escalation is immediate become mission-threatening in a spacecraft where no one is awake to escalate to. The research community studying this problem is aware of the gap between the components and their integration. The work in clinical hypothermia and synthetic torpor pharmacology is real and making progress. The integration question, how to combine those separate advances into a system that works reliably in the spaceflight environment, is the research problem that has the most distance yet to close. A parallel challenge exists in establishing what successful recovery looks like after pharmacologically managed multi-month torpor. Returning astronauts already undergo structured medical assessment before resuming active duty. That assessment typically extends over days or weeks. Recovery from 6 months of induced metabolic suppression would require a similar process. But the clinical reference for what states are expected after this specific experience does not yet exist. No human has been through it. The expected recovery range and the thresholds between normal recovery and a complication requiring intervention cannot be established from existing literature because the experience is novel. This matters for mission planning as well as crew safety. A recovery protocol requires specific timelines and functional thresholds to guide decisions about when the crew is ready for critical work. Without human data about what induced multi-month torpor actually produces in the body, those specifications must come from extrapolation rather than observation. A mission that cannot distinguish normal recovery from a developing complication at the moment when crew capability is needed carries a risk that the earlier mission phases succeeding correctly does not resolve. That is not a reason to stop, but a reason to be honest about what stage the concept is in. The components are further along than they were a decade ago, but the integrated system is still a research goal, not a development program. The final question is not whether the body can become quiet. It is whether it can wake useful. The display shows the spacecraft days from the destination orbit when the eyes opened slowly. The body inside is warm again, temperature rising under the pod's rewarming protocol for hours. Vital signs are stable. But the person in the pod has not eaten a full meal in 6 months, has not moved purposefully, has not made a conscious decision, and has not exercised or spoken in all that time. What happens next is not a cinematic cut to mission operations. It is a medical process with its own timeline, its own risks, and its own place in the mission architecture. ESA's architecture study includes a 21-day recuperation period after the 180-day cruise phase. That number is a planning assumption built directly into the mission design, not a buffer of convenience. It is a recognition that recovery from a 6-month torpor state is itself a mission phase, one that takes real time, requires managed care, and has to be substantially complete before the crew is ready for mission-critical work. The 21-day figure comes from the best available analogues, clinical hypothermia recovery data, outcomes from extended sedation in intensive care, and what is known about deconditioning recovery from prolonged bed rest and microgravity exposure. It is not a precise measurement from a human torpor study, because no human torpor study of that duration exists. It is an estimate based on what the nearest analogues suggest about how the body transitions back to full function after extended metabolic suppression. The real recuperation timeline could be longer depending on complications that occurred during the cruise, the individual's baseline, and factors that cannot be anticipated in advance. Rewarming is the first phase. core temperature rising from the torpor range back to normal does not happen instantly and cannot be allowed to happen without management. The rate of warming matters. Too fast and the body's chemical systems reactivate unevenly, potentially producing cardiovascular instability or other complications. The pod's thermal system manages the rewarming rate, but the crew member's own biology plays an increasingly active role as temperature rises. Monitoring during this phase is as intensive as at any other point in the mission. As temperature normalizes, metabolic systems begin to reactivate. Digestive function returns slowly as the gut resumes processing food after months of suppression, with nutrition shifting gradually from the parenteral delivery that supported the torpor state to more normal intake. Hormonal systems re-establish normal circadian and regulatory rhythms, while the immune system reactivates in ways that may briefly overshoot as the inflammatory responses suppressed during dormancy return to normal operation. Muscle weakness after 6 months of largely immobile dormancy is one of the most predictable effects, even under the most optimistic assumptions about torpor providing some degree of protection against microgravity-related deconditioning. The combination of inactivity and weightlessness over 6 months produces deconditioning that requires progressive rehabilitation. Standing, walking, and performing physically demanding work require a rebuilding period. The rate of recovery depends on the individual and on what happened during the cruise, but it cannot be compressed to zero. Physical therapy, progressive loading, and structured exercise rehabilitation are part of the recuperation plan. Cognitive function follows its own recovery arc. Sedation, metabolic suppression, and extended dormancy all affect the brain's operational readiness. Medical literature on patients recovering from prolonged intensive care sedation describes periods of disorientation, slowed processing, and altered judgment that can persist for days or longer. The severity and duration depend on factors including sedation depth, total duration, and individual baseline. A crew member recovering from a 6-month torpor state is navigating some version of this process in a spacecraft approaching a planetary destination, with no immediate support from Earth and mission-critical work beginning within weeks. Infection and clotting risks do not end at wake-up. They remain elevated during the early recuperation phase. The immune system reactivating after suppression may initially be less effective than normal at surveillance and response. Blood clots that form during dormancy may become more mobile during the physical changes of rewarming. Complications that were pharmacologically suppressed during the torpor phase may become clinically apparent as the suppression lifts. The medical monitoring systems cannot stand down when the crew wakes. They have to continue through the recuperation period, watching for problems that the dormancy itself may have deferred. A cognitive and psychological dimension also exists that is genuinely hard to anticipate from any existing clinical reference. A crew member who was in deep space for 6 months without awareness opens their eyes to find themselves approaching a destination they were last conscious of leaving. The mission has been proceeding without their participation, the spacecraft making decisions for them, their physical condition managed entirely by machines. The psychological experience of waking from 6 months of dormancy into full situational awareness near a distant destination has no precedent in human medicine or spaceflight history. Astronauts returning from the International Space Station go through a carefully supported landing day sequence with medical teams, gravity adaptation procedures, and the immediate comfort of being on Earth with full support available. A crew recovering from torpor near Mars has none of those supports. Communication delays make real-time consultation with Earth impractical for time-sensitive decisions during the early recuperation. They have each other and the spacecraft's systems. ESA's 21-day recuperation period builds this reality into the mission architecture. The crew does not become operational on the day they wake. The spacecraft's autonomous systems have to continue managing the mission through the recuperation period because the crew cannot immediately take over full operational responsibility. The transition back to full human command of the spacecraft is a managed, gradual process. Understanding this changes how to think about the net benefit of the torpor concept. It is not a way to arrive fully ready, It is a way to arrive having spent less mass, consumed fewer supplies, and avoided the psychological burden of 6 months of active confinement while building in a recovery phase of its own. The net benefit has to be assessed against the full picture, including the time cost and risk of the recuperation period. The training question adds one more dimension. Crew members preparing for a torpor mission have to train for tasks they will perform after a 6-month dormancy with an uncertain recuperation period, in a condition they cannot fully simulate on Earth. Astronauts preparing for conventional missions can simulate microgravity in neutral buoyancy facilities, run vehicle procedures in high-fidelity trainers, and work countless contingency scenarios in controlled environments. Preparing for post-torpor operations is harder to simulate, because the physiological state of a person recovering from 6 months of pharmacologically managed metabolic suppression under spaceflight conditions has no terrestrial analogue. Training for the recovery phase is partly a matter of planning and protocols, and partly a matter of designing the mission to work within the realistic capabilities of recovering crew members. ESA's 21-day recuperation period is built into the mission architecture with this in mind. The crew is not expected to operate at full capacity the day they wake. The plan accounts for gradual return to function. That planning assumption is itself a significant engineering and operational constraint. The mission has to succeed with crew who are recovering, not crew who are at their peak during the early phase after arrival. Only now, with the recovery phase understood as part of the mission rather than its conclusion, can the question of what hibernation might actually make possible be answered honestly. The pod from the beginning of this inquiry is still the right place to return to. That same small chamber in the dark spacecraft, the same monitored body breathing steadily inside it, alive and slowed. Understand it now with everything that has been covered. The pod is both a promise and a problem. That combination is what makes the answer honest and what makes it harder than a yes or a no. The promise is real. A spacecraft designed around that pod, and 5 more like it, can be smaller and lighter than a conventional habitat. ESA's assessment found roughly 1/3 less mass under the study's assumptions, and SpaceWorks proposed to transfer habitat at 5 to 7 metric tons against 20 to 50 for conventional designs. The consumables reduction follows directly, as does better shielding geometry when the crew is concentrated in one small volume, and the psychological burden of 6 months of active confinement is replaced by something the crew mostly does not experience. These benefits rest on real architectural logic, studied with care by serious engineering groups, and the numbers are genuine projections from real mission parameters. The problem is equally real. Radiation accumulates in the hull and tissue, regardless of whether the crew is conscious of it, and while concentrated pod shielding helps with geometry, it cannot eliminate the chronic galactic cosmic ray dose, or provide the biological radio resistance that animal experiments hint at, but have not demonstrated in humans. Microgravity still acts on the body regardless of metabolic rate. The pod requires automated management of 6 patients for 6 months without staff or real-time consultation, and the recovery period at the end takes 3 weeks or more as a mission phase in its own right. These are not objections to the concept as a direction of research. They are the actual engineering and medical requirements that the concept has to satisfy before it becomes operational. The bounded verdict that the evidence supports is this: torpor-like states could become a serious mission architecture tool for deep space transfers before they become anything like science fiction cryosleep. That sentence has a specific shape, and it is worth staying with each part. The sentence carries 3 qualifications: could rather than will names the uncertainty, before they become separates the near-term tool from longer-term speculation, and mission architecture tool limits the claim to changing the mass and volume equations for a specific class of mission. The strongest version of the concept reduces the mass and crew burden of a deep space transfer without removing the radiation, microgravity and recovery costs that remain whether the crew is active or dormant. The question is whether the architectural savings outweigh the added complexity of managing a crew in torpor autonomously for the full duration of the cruise. For a Mars-class transfer, The case for studying the concept seriously is well established. The architectural numbers from ESA and SpaceWorks are substantial enough to justify continued research. The medical challenges have identifiable pathways in clinical medicine and autonomous systems engineering, and the biological evidence from hibernators and synthetic torpor gives the concept a foundation that is not fictional, reinforced by the analog in clinical medicine, confirming that human metabolism can be influenced under the right conditions. The research trajectory that makes the bounded verdict meaningful is incremental. Human subjects' studies of mild induced metabolic suppression are feasible in clinical settings and would establish the baseline that animal studies alone cannot provide. Autonomous monitoring hardware capable of managing one patient for a week could be extended incrementally, with each stage testing reliability under more demanding conditions before the next begins. Each step builds the evidence base that the next step requires. The outer planet boundary deserves specific attention because it tends to get folded into discussions of the Mars concept as though it was simply an extension. For missions to the outer solar system, the challenge is not only that supporting evidence does not scale to multi-year durations. Architecture changes in ways that compound every problem at those durations. Longer transfer time accumulates more radiation regardless of biology. More years of autonomous operation create more opportunity for novel failure modes. A crew waking after years rather than months faces recovery demands that have no clinical reference. Duration at these scales changes the nature of what has to be demonstrated rather than simply its magnitude. This does not rule out outer planet torpor architecture as a very long-term prospect. It clarifies why the near-term research case rests specifically on Mars-class transfers and why extending the claim to longer durations requires evidence that does not currently exist. For outer planet missions measured in years, the case becomes progressively more speculative. The same architectural logic applies in principle, but the supporting evidence does not scale to the longer durations, and the reliability requirements grow far more demanding over multi-year timescales. For decade-scale or century-scale scenarios, the concept reaches a speculative boundary, worth knowing about and thinking through, but not validated by current evidence, and not appropriate to present as a near-term prospect. The honest answer does not satisfy the fantasy. Science fiction offers cryosleep as a way to make vast distances irrelevant and journeys invisible. Real science offers something more limited: the possibility that managed dormancy could reduce the cost of specific deep space missions without erasing the biological toll of the journey. That is a smaller promise. It asks for appreciation of what specific numbers and concepts actually establish, versus what they leave open, and for the ability to hold genuine promise and genuine limitation in the same sentence without simplifying to one conclusion. The temptation to simplify is real. The cryosleep end says the crew just goes to sleep and the mission becomes easier. The dismissive end says hibernation is science fiction. Both are wrong. The ESA and NASA/SpaceWorks studies represent serious engineering work. The biological challenges represent real and unresolved requirements. And the honest position is exactly in the middle, promising enough to study carefully, demanding enough not to pretend it is solved. The pod is still there, the body inside it still crossing space, the machine watching over it still running its monitoring cycles. Radiation is still accumulating outside the hull, regardless of whether anyone inside is counting it, and the spacecraft is still making its own decisions in the silence. A second-order value in the bounded verdict is easy to miss. By keeping the claims honest, the research field stays open for the advances that matter. Overselling the concept before it is ready produces disappointment that damages credibility and makes sustained investment harder to secure, while dismissing it as science fiction leaves real architectural benefits unstudied. The bounded verdict is both intellectually honest and strategically correct for the long-term development of the capability. The deep space future that torpor research is working toward is not the movie version. It is quieter, harder, more conditional, and more medically demanding. It is also, on its own terms, a remarkable prospect. The human body might one day travel through space at a fraction of its normal metabolic cost, arriving changed but alive and ready for the work that makes the distance worth crossing. Return to the quiet body and the machine keeping watch. The dark transfer habitat is the same one from the beginning of this journey. It is a small volume with dim instrumentation light and a monitored body breathing in its pod. It is quieter now because we know more of what surrounds it. The picture has filled in. Outside, galactic cosmic rays are still moving through the hull. The particle flux does not wait for anyone to be awake. Inside, the automated systems run the monitoring cycles that keep the body stable, while the spacecraft works through its own operational checks, maintaining trajectory and watching for anomalies. From here, the Sun is a hard-edged point of light, smaller than any memory of it from Earth, still pulling the spacecraft through its transfer orbit. Deep space travel without the fiction stripped out looks like this. Not a glowing cryotube, but a piece of medical engineering surrounded by all the hazards that the mission was designed to manage, only partially. The journey cannot be skipped. That is the hardest thing the pod teaches. The spacecraft problem, the mass and consumables and the psychological burden of months of active confinement might be reduced by torpor architecture if the biology can be made to work. The engineering groups that studied this found genuine and quantifiable benefits. A lighter spacecraft with better shielding geometry, lower consumables for mostly inactive crew, and less accumulated confinement stress at arrival. Those are not invented benefits. They follow from the arithmetic of what deep space missions cost to build and fly, and what a human body costs to keep active in a closed environment for months. But the body problem does not disappear when the crew is asleep. Radiation keeps accumulating in the cells of a dormant body regardless of the crew's awareness. The body in weightlessness keeps adjusting to the absence of gravity, and the medical management requirement does not simplify when the patient is quiet. Temperature, immune monitoring, and every operational decision that would normally involve human judgment must still be handled by the spacecraft's systems without interruption. Each of those constraints is a live problem, not a theoretical concern, but a real engineering and biological challenge that has to be solved reliably before a torpor mission leaves Earth. Consider what it would mean to close any one of those gaps. A validated protocol for safe human metabolic suppression over weeks would contribute to critical care medicine well beyond spaceflight. It would extend the protective window available after certain acute injuries, the window during which reduced metabolic demand limits secondary damage while the primary injury resolves. The monitoring technology developed to manage a dormant crew through months of physiological variation without clinical staff would represent a new category of autonomous medical system. Research driven by the space requirement tends to produce tools whose value extends beyond the missions that motivated the work. The biological picture from natural hibernation and synthetic torpor research does not provide a blueprint, but it is also not nothing. It identifies where to look. At the metabolic pathways that evolution refined across millions of years in hibernating species, at the cellular mechanisms that preserve muscle and bone through weeks of inactivity, at the molecular adjustments that shift energy use from normal activity to slow fat oxidation during torpor. Each of those mechanisms is now understood at the molecular level. That is a different foundation than existed a generation ago. The distance from that molecular understanding to a clinical application is measurable in research steps rather than in fundamental unknowns. The question remaining is one of timing and parallel development. The research required to close the gap does not have a defined completion date. The missions that would use the capability are being designed now, not in an abstract future. Architecture decisions locked in today will determine what kind of transfer habitat gets built for near-term Mars missions. If the research converges in time to inform those decisions, torpor becomes a real option. If it converges later, the benefits extend to subsequent missions but not the first. The research and the mission planning are proceeding on separate schedules, with the outcome depending on which advances arrive in time to matter. That uncertainty is not unusual in the history of spaceflight technology. Every system that defines modern deep space operations was once theoretically motivated and technically unresolved, waiting for sustained investment and accumulated knowledge to close the gap. The published research describes what is known and what remains unresolved with precision that makes honest evaluation possible. The work is being done with the seriousness the problem deserves. That the answer is not yet available is the normal condition of a research question that has not finished being answered. The gap between the concept and the capability is not an argument against pursuing the research. It is the honest description of where the field actually stands. Natural biology demonstrates that mammalian physiology can manage remarkable low metabolic states with genuine protective benefits, and synthetic torpor research suggests that this biological machinery may not be limited to naturally hibernating species. Clinical medicine further confirms that human metabolism can be managed under controlled conditions. Each of those observations gives the question a real scientific foundation. But foundations are not the same as finished work. The animal evidence is animal evidence, not a human mission blueprint. The clinical hypothermia evidence works under intensive supervision, not autonomous deep space management, and the synthetic torpor experiments are brief laboratory demonstrations, not validated protocols ready for mission development. The sleep is a way of traveling through the journey while some of its costs are deferred or reduced. Not all of its costs. Radiation does not defer because the traveler is unaware of it. Medical monitoring requirements do not simplify because the patient is quiet. And the spacecraft does not become easier to operate because the people who would normally operate it are unavailable. What torpor might eventually make possible is a lighter, leaner version of deep space travel that carries less of the daily human cost of the transfer phase. What it cannot do, now or in any foreseeable near term, is make the journey something other than what it is. A long crossing through a radiation-filled, weightless environment that the human body was not designed to cross and cannot be made fully safe for by any single technique. The history of human exploration is a series of discoveries about what cannot be avoided. Flying faster does not prevent altitude sickness, and swimming faster does not prevent decompression sickness. The biological costs of deep space travel are not going to be avoided by putting the crew to sleep. Some of them might be reduced if the biology and engineering can be made to work together. That is a meaningful prospect, and also a genuinely different claim from the one that science fiction makes. The body inside the pod may sleep all the way to Mars if the research succeeds and the mission architecture comes together and the autonomous systems work and the recovery period plays out the way the plans assume. Space will not sleep with it. Radiation will keep accumulating. Microgravity will keep acting on cells and fluid and bone, and the machines will keep working or failing while the universe remains exactly what it has always been, indifferent to whether anyone is awake enough to notice. The body may sleep, but space does not. The pod is still small. The monitored body is still inside it, crossing real space in the dark. The instruments keep their readings. The spacecraft keeps its course. Everything that was true at the beginning is still true. What has changed is the picture surrounding that pod. At the beginning, the image carried a promise borrowed from science fiction that the journey could be made to disappear by making the traveler unconscious of it. That promise was worth examining carefully because the curiosity is real and the question behind it is genuinely important. Could sleeping through deep space make deep space travel actually possible? Could the biology of dormancy transform what is currently an extraordinarily demanding and dangerous crossing into something the human body can survive, perhaps even comfortably? The honest answer is bounded, and that boundary is not a failure of ambition. It is the shape of what the evidence actually supports. Torpor-like states may one day help make some deep space missions more practical. Not all missions, not missions of any duration, specific missions, Mars-class transfers measured in months, with a carefully designed habitat and autonomous medical systems and a structured recuperation period, might benefit from reduced habitat mass, lower consumables, better shielding geometry, and less accumulated confinement burden. Those are real benefits, supported by real architecture studies from real engineering groups. The incentive to continue developing the concept is genuine, but hibernation is not operational cryosleep. Nothing demonstrated in current science supports putting a human being into suspended animation and retrieving them intact after months or years. The closest real analog, clinical hypothermia under intensive care, works for hours under constant medical supervision. It is a foothold, not a destination. The animal evidence is genuinely interesting, but it is animal evidence, and the translation to human subjects under spaceflight conditions has not been made. The hazards that survive even a sleeping crew are not small. Radiation keeps accumulating. Microgravity keeps acting on muscles, bones, fluids, and vision. Blood has to be managed to prevent clotting. The body has to be fed, monitored, and maintained over months by automated systems that have to work without error, without maintenance, and without the ability to ask for help. The spacecraft has to run itself through everything that might happen during the cruise, and the recovery at the end is a mission phase, not a cinematic moment. Those are not objections to the concept. They are the actual requirements that the concept has to satisfy. Meeting them would represent a genuine scientific and engineering achievement. Not meeting them, assuming they are solved before they are actually solved, is how missions fail. The recovery phase adds one dimension that no cinematic version of the story includes. Waking from months of torpor is not stepping out of a chamber restored. It is a structured medical period during which body temperature, metabolic rate, and physical function return to levels compatible with active work. The crew arriving at Mars has been through a medical process, not a rest. Their readiness for mission work depends on that process having gone correctly, and the mission timeline has to account for it explicitly. The sleep is a way of crossing the distance. It is not a way of escaping the distance. The pod in the dark spacecraft is a real object of inquiry. The research behind it is serious. The benefits it might provide are substantial enough to study. The hazards it does not remove are honest and clear. That combination, genuine promise, genuine limitation, genuine honesty about where the line falls, is what good space science looks like when it engages with a question that popular imagination wants to simplify. The body inside that pod may sleep all the way to Mars. Space will not sleep with it.